Have you ever looked around and thought, is this all there is? Our world feels so solid, so complete. We've got length, width, and height, 3 dimensions. But what if I told you that our entire reality might just be a shadow of something much, much bigger? Welcome to the 4th dimension. Now, before your brain starts to melt, let's get one thing straight. When we talk about dimensions, we're just talking about directions. Think about it. A single point is 0-dimensional. It has no direction to go. Draw a line, and you've created 1 dimension, length. You can move forward or backward. Add a second line at a right angle, and suddenly you have a flat surface. A 2-dimensional world with length and width. This is the world of video games like Pac-Man, or drawings on a piece of paper. Now add a 3rd direction, height. Boom! You're in our 3D world, where you can move left, right, forward, backward, and up, down. Our brains are hardwired for this. We've evolved to navigate a 3D environment, to judge distances, and to catch a ball coming at us. It's our natural habitat. So, where does the 4th dimension fit in? Logically, it would be another direction, perpendicular to the other 3. The problem is, we can't point to it. We can't see it. Our senses are completely blind to it, but just because we can't see it doesn't mean we can't understand it. Let's use an analogy. Imagine a world called Flatland, inhabited by 2-dimensional shapes, squares, circles, triangles. They can move left and right, forward and back, but up is a meaningless concept to them. Now imagine you, a 3D being, gently push your finger through their flat world. What would they see? They wouldn't see a whole finger. They'd see a mysterious circle that appears out of nowhere, maybe grows a little wider, and then shrinks and vanishes. They would be baffled, maybe even terrified. They can only perceive the 2D slice of your 3D finger. Well, we are the Flatlanders in this scenario. A hypothetical 4-dimensional object passing through our 3D world would appear just as strange to us. We would only see a 3D cross-section of it, changing shape and size in ways that seem to violate our laws of physics. We can't perceive the whole 4D object, only its 3D shadow. Mathematicians and physicists have a name for the 4D equivalent of a cube, a tesseract or hypercube. We can't build one, but we can project its shadow into our 3D space, just like a 3D cube casts a 2D shadow on the ground. When you look at a rotating tesseract animation, it seems to warp and turn inside out. That's not the tesseract itself warping, it's just the distorted 3D shadow of a perfectly rigid object rotating in 4-dimensional space. The same way a cube's shadow stretches and shrinks as you turn it in the light. Now, this is where things get really interesting, because the 4th dimension isn't just a geometric curiosity, it's fundamental to our understanding of the universe, thanks to a guy you might have heard of, Albert Einstein. Einstein had a revolutionary idea. He suggested that the 4th dimension isn't another spatial direction like length or width, but is, in fact, time. He unified the 3 dimensions of space and the 1 dimension of time into a single 4-dimensional fabric called spacetime. Think about it. You are always moving through time. Even when you're sitting perfectly still, you're hurtling into the future at a rate of 1 second per second. In Einstein's model, your movement through the universe is a combination of your motion through space and your motion through time. This is the core of his theory of relativity. And it comes with a mind-bending consequence. The faster you move through space, the slower you move through time relative to a stationary observer. Imagine you're in a spaceship traveling near the speed of light. From your perspective, everything feels normal. But to someone back on Earth, your clock would appear to be ticking incredibly slowly. You are trading your speed through time for speed through space. This isn't science fiction. It's a proven physical effect called time dilation. GPS satellites have to account for it every single day, or their clocks would become inaccurate, and your navigation app would send you miles off course. Spacetime isn't just an abstract idea, it's a physical reality that affects our technology. For Einstein, gravity itself isn't a force pulling things together. It's a curvature in the 4D fabric of space-time caused by mass and energy. A planet isn't being pulled by the sun. It's following a straight line through curved space-time. Our Earth is just rolling along a groove that the sun has warped into the universe. But what if time isn't the only other dimension? What if there are more spatial dimensions, just like length, width, and height? This is where we venture into the cutting edge of theoretical physics, with ideas like string theory and M theory. These theories propose that there might not be just 4 dimensions, but 10, 11, or even more. So where are they? Why can't we see them? The leading idea is that these extra dimensions are compactified. They are curled up into incredibly tiny subatomic shapes, far too small for us to ever perceive directly. Imagine a long, thin garden hose. From far away, it looks like a one-dimensional line. But if you get very, very close, you realize it has a second dimension, its circumference. You could have a tiny ant walking in circles around the hose, exploring a dimension that was invisible from a distance. String theory suggests that every single point in our universe might contain one of these tiny, multi-dimensional shapes. The fundamental particles that make up everything, electrons, quarks, photons, might not be points at all, but tiny, vibrating strings or membranes wiggling around in these hidden dimensions. The way they vibrate determines what kind of particle they appear to be. It's a beautiful, elegant idea that could potentially unite all the forces of nature into a single theory of everything. Thinking in 4 dimensions, or even more, completely changes how we see the universe. It allows physicists to model incredibly complex phenomena. The concept of hyperspace in science fiction, where ships take shortcuts through the galaxy, that's based on the idea of folding higher dimensional space to connect 2 distant points. Even in our daily lives, the math of higher dimensions is crucial. Data scientists and AI developers work with high-dimensional spaces all the time. When a program analyzes thousands of variables to recommend a movie or identify a face, it's navigating a mathematical space with thousands of dimensions. So, why does any of this matter? Because understanding the 4th dimension is about more than just mind-bending puzzles. It's a lesson in humility. It reminds us that our perception of reality is limited by our biology. The universe might be infinitely richer, more complex, and more beautiful than our 3-dimensional minds can ever fully grasp. What we experience might just be a faint echo, a pale shadow of a grander, higher dimensional reality. It's not just a concept for sci-fi movies. It's the language modern physics uses to write the story of the cosmos, from the Big Bang to the fate of black holes. The 4th dimension isn't just out there. It is woven into the very fabric of everything. Thanks so much for exploring the universe with me today. If this blew your mind, be sure to hit that like button and subscribe for more journeys into the frontiers of science. Let me know in the comments what concept you'd like to dive into next.